Thank you very much, and thanks for coming out here on this Saturday morning to hear about math and food. I'm going to talk about math and food because I love math and I love food. And unfortunately, some people seem to like food more than they like math. But seeing as you're all here, I expect you all love math. Who loves math here? Do you love math? Yay! I love that. That's fantastic. So I'm going to show you some of my favorite mathematical structures that you might not have thought of as being anything to do with math. Because actually, math isn't just about numbers and things like that. It's also about all sorts of things. And actually, math is everywhere in the world around us. And I think that sometimes people say to me, I have lots of friends who have children, and they say to me, they know that reading books is a good thing to do with the family, but how do you do math at home with the family? Do you just sit around at home and add numbers together? Well, some children really like adding numbers together, but there's so much more you can do than that. So I'm going to show you some of the things, including I'm going to show you that math is just the study of how things work, anything. And if you're interested in how things work, then you can be interested in math. Of course, really, it's not the study of how any old things work. It's the study of how logical things work. And it's actually not any old study of how logical things work. It's the logical study of how logical things work. And the trouble with that is that nothing behaves logically. I don't behave logically. I bet you don't behave logically. Do you behave logically? This computer definitely doesn't behave logically. Nothing actually behaves logically. And so in order to study anything logically, we have to forget the pesky details that stop things behaving logically. And that moves us from the real world into the abstract world of ideas. Instead of real objects, we have ideas about objects, and that's where logic really does work. And the great thing about this world is that as soon as you have an idea for something, you can play with it. You don't have to beg your parents to buy you the Ninjago Lego set, which is what my nephew really wants at the moment. Please, can I have the Ninjago Lego set, please? You don't have to beg. As soon as you have the idea for something, you can play with it. And I wish that as soon as I had the idea for my dinner, it would just exist and I could eat it. But with math, as soon as you've thought of it, you can play with it. The other good thing about it is that lots of things become the same when you do that abstraction. Just like if you have one cookie, that makes two cookies. And if you have one apple, that makes two apples. And if you have one monkey and another monkey, that makes two monkeys. And then you go, hey, wait a minute. It didn't matter that those were apples and monkeys and cookies. It could be one anything and one something else, and that makes two of those things. And so you go, well, why don't I just call that 1 plus 1 equals 2, and then you have performed an abstraction. You've moved from the real world of objects into the abstract world of ideas, where everything works. Now, the thing about that is that you don't really have your feet on the ground anymore when you're in the abstract world, which can be a bit scary. But I think it's a bit like flying. Now, I don't want to fly, really. I don't think I would dare ever jump out of a plane and do real flying or skydiving or anything like that. But I love intellectual flying. And that's what I feel like I'm doing when I'm doing math. I'm flying around in my ideas, and I like that. Now, some people don't like it because in the abstract world, you can't win arguments by yelling. And some people like winning arguments by yelling. And that doesn't work in the mathematical world. But I don't like winning arguments by yelling, so I prefer the mathematical world. So I'm going to show you some of my favorite things. And the first of my favorite things I'm going to show you is the mathematics of this piece of Bach. Bach is one of my favorite composers. And Bach has a lot of math inside it, so much that I could probably talk about that for about 3 weeks without stopping, just by itself. So I won't do that. But Bach wrote a lot of math into his music, actually. And in this piece, well, I'm going to show you, but it's one of the 48 Preludes and Fugues he wrote that's part of the Well-Tempered Clavier. And he wrote these pieces because it had suddenly, well, not suddenly, but it became possible to play music in every key. Before that, some keys sounded really great, and some keys sounded really terrible, so you had to avoid them. But then, using some math, they found a way of making every key sound quite nice, and Bach got really excited about this. So he wrote one prelude and fugue in every key. There are 12 keys on the piano, so that makes 12. He wrote in major and minor, so that makes 24. And then he got really excited and did it all again, so that makes 48. So this is from the second book where he got really excited and did it again, and it's the Prelude in G minor. I'm going to start by playing it for you. Thank you. It's very exciting for me to get to play the piano here. I've come to see several shows here. I came to see the Nutcracker here just before Christmas, and I came to see Tosca here before that, and so it's funny being on this side because I've been on the other side before. So I hope that you will also come and see some great shows that they have here. So this piece of Bach is written in polyphony, which means that there are several different lines of music, and they wind their way around each other, so that you could get 4 people to sing it, possibly, because the lines of music are slightly different. So the first line goes like this, just sits there for a while, and then the next one goes, and then the next one goes, and so on. And usually when you study a piece of polyphony, you start by isolating each line of music and maybe singing it yourself to see where it goes. And when I first studied this piece, I got really confused by it. And I discovered that I couldn't really tell where the lines of music were. So I decided to draw a picture of it. And the picture came out like this. So this top line, this black line here is the one at the top. But as you can see, it kind of slides down. This you might call the soprano, that's the highest voice in a choir. And it slides down and ends up as the tenor. And the alto slides down and ends up as the bass. Whereas this bass line here, the one that started ba, this one slides up and ends up as the alto, and this tenor line ends up as the soprano, which makes it a bit difficult to get 4 people to actually sing it, because they'd have to be able to sing soprano, alto, tenor, and bass. I know one person who can do that, but that's a bit unusual. Now, when I drew this picture, I understood why I didn't understand the piece. And that's often the first step to understanding something, is understanding why you don't understand it. Because the lines cross over each other and they don't come back again. And so I lost track of them as I went along. And once I had drawn this picture, I reckon I can play the piece of music better. This is a very abstract version of the piece where I have forgotten almost every detail apart from where the lines of music are in relation to each other at any given moment. And now that I've got the abstract structure, I can play the piece better. Now, you didn't have to see the picture in order to listen to the piece of music. And that's the thing about math. It's everywhere. You don't have to know it's there in order to go about your life. And sometimes people say to me, you know what, I get on perfectly fine without math. And I say, yeah, but I get on better. And it's just like, you don't need to know how this building was built. You don't need to know where the structural walls are in this building in order to come into the building and use it. But it's a good thing that someone knows where the structural walls are. And if you understand how something works, you can use it better. You can make up your own version of it. You can create something from it that works better. You can fix it if it's broken. There's so much more you can do if you understand how something works. And that's why I like understanding how things work, so that I don't have to go and get someone else to fix things and make things for me all the time, because I much prefer making my own things, whether it's making my own music, making my own food, drawing my own pictures. Next, I would like to talk about juggling. Now, I'm not very good at juggling. I used to say I can't juggle, but someone said to me, you know, that's like what people say about math when they just say, I can't do math. And I thought, oh dear, that's true. But I'm still not very good at juggling, and probably not good enough to do a demonstration in front of an audience. So I'm wondering if there's someone here who would be able to do a juggling demonstration for me. Yes, wonderful. Please do come up. Hooray! And you're wonderfully dressed for the part. What's your name, if I may?
My name is Kent.
Kent, thank you so much.
Oh, I thought you said mugging.
Really?
It's the only word I could think of that rhyme with juggling.
Oh, muggling. No, go for it.
So everybody can juggle one ball, because you just throw from one hand to the other. Can everybody do that? That's as far as my lesson ever went. So you just learn to throw one ball, and then you learn to throw two.
So this is the problem. I'm not very good at throwing or catching, so please go ahead.
So that's why you practice one for a
I
long
practiced for a really
time.
long time. Please do that, please.
So the third, the jug, the actual jug we want, right? So now we
Thank
now
you.
you could throw it over. So there's a juggling lesson.
So please just do the juggling.
Oh, you want me to keep juggling?
Yes. Would you mind walking across the stage while doing it?
You can try.
Woo! Now, everyone please imagine that there's a long exposure camera taking one picture of Kent as he walks across the stage, so that each ball is becoming a path through the air. And can you imagine, without the dropping part, can you imagine what picture it will make as he does it? Thank you very much. A round of applause for Kent.
Thank you.
Thank you. Can you imagine what picture that made? So here is one that I made with some illuminated juggling balls in a dark room. It was not me who did this juggling. The one I did was very wonky, so it was an 8-year-old boy who did this. So here's one that I made digitally, and now we'll do a very hilarious juggling demonstration. So imagine that I have the green and the red ball in my right hand. So I'm going to start by throwing the green one across, and as it goes, the blue one starts coming across. And as the blue one is going, then the red one starts coming across. And then as the red one is going, the green one comes across. And so it makes this pattern. And if I turn this picture sideways, then you can see it's the same as the braid in my hair. And this is something that mathematicians study. They're called braids. And this was very funny because I had drawn the picture of the braid when I was studying my Bach piece, and I didn't know it was something mathematicians do. And I drew that picture before I started my PhD. And when I started my PhD, one of the first papers I read had pictures like that in it. And I went, wow, it's like that picture I drew for my piano piece. Everything starts becoming united. And one of the things math does is it makes connections between situations that seem unconnected. And I love seeing connections between things, and I love making connections with people. And I think we spend too much time sometimes in the world showing how different we are from everyone instead of making connections with things. And math is a very unifying subject. So I once tried to braid my hair like this Bach braid. And you might see it doesn't work at all, because you would need a band here, a band here, a band here. This green strand's just floating around doing nothing. Whereas in the normal braid, you only need one band. And you can see if I take it out and then I kind of pretend I'm in a shampoo commercial, then I always wanted to be in a shampoo commercial when I was little. Then you can see the whole thing was only held in by one band. And that's because it's looped up enough that it will stay together, whereas this one is hardly looped up at all. And mathematicians study these things, and they study how looped up they are. And they study things like, if I wave that green strand around, it will turn into some other braid, but it won't really be different, because all I did was wave it around. Whereas this one, in order to change it, you really have to undo it and redo it. So mathematicians say, what makes it really different? How do we tell which ones you could turn into others without taking the band out? And this started off just as a piece of fun, and curiosity is what drives a lot of mathematics. If you're just curious about something, and then sometimes it becomes useful later. And with this might be useful for early diagnosis of Alzheimer's disease, which might be related to the way that brain cells are tangled up. And the idea is maybe they become mutated and tangled up in the wrong way. And then you need a way of being able to tell whether the tangle is the same one from a different angle or really genuinely different. And you can't just stick your finger into someone's brain and pull out a brain cell and wave it around. So math gives you an abstract way of studying that. But that use for braids really came later. And the first reason that mathematicians did it was just kind of for fun. And this is often the case with math. So we often stress how useful math is, which I think is a shame, because it doesn't make it sound interesting. It's like saying, I'd like you to meet my friend. They're really useful, which is not something you'd usually say about a person. Whereas the math that was done 300 years ago in number theory is now what's at the basis of cryptography in the internet. That took 300 years. The Platonic solids are from 2,000 years ago, and one of them, the icosahedron, had no use until the 1950s, when microscopes were made that were powerful enough to look at viruses, and a lot of viruses turned out to have the structure of an icosahedron. So that took 2,000 years for a use to be found. So I think that shows we should be happy to study things just because they're interesting sometimes, and that uses will follow later. So because I couldn't braid my hair like this, I made a pie instead. This is my Bach pie. It's banana and chocolate. Banana and chocolate. So now I'd like to talk about something that's more obviously mathematical, the factors of 30. So maybe we can remember what the factors of 30 are. What numbers go into 30? Well, there's 1, 2, 3, 5, 6, 10, 15, and 30. Very good. It's not very interesting. It's a bunch of numbers in a straight line. And we live in a three-dimensional world. So we write on two-dimensional pieces of paper in one-dimensional straight lines. And sometimes we squash all our math into a one-dimensional straight line, and we lose natural geometry that it already had. And I like to say this is why I don't tidy the papers on my desk, because they have a natural geometry. I don't want to squash them into one dimension. So here I'm going to rediscover some of the natural geometry of this situation by drawing a kind of family tree to show which numbers are also factors of each other. And so 30 is like the great-grandparent at the top. Then I have 6, 10, and 15 that all go into 30 without anything in between. Then there's 5 goes into 10 and 15. 2 goes into 6 and 10. 3 goes into 6 and 15, and 1 goes into 2, 3, and 5. So now we see it's a cube. And it's a cube not the usual way up, but standing on one corner. And I think this is much more interesting than a bunch of numbers in a straight line. And it's also related to braids, because if if this is really a cube, I can wrap it up like a present. And I'm going to wrap it up with different colors of ribbon. So here I'm going to use red and blue, and the red coming in from the right is going to be on top. So the red is now going to follow down the side here, and the blue is going to follow down here. And then I need a third color to come around the side, so this is green. And on the other side, I'm going to do the same thing, but the blue, the red, and the green will start in the same places, but this time they'll follow the pattern on that present. So that makes this. And now maybe you can see that if I shuffle this green braid up and shuffle the red and blue crossings down a bit, this braid here will become that braid over there. So they're actually what mathematicians would call the same braid. But it all comes from wrapping up a present, a cubical present. And this is something that, again, that I saw when I was doing my PhD. And this is a very fancy piece of math. That braid thing is called the third Reidemeister move. Mathematicians give fancy names to things, kind of to make ourselves feel clever. And unfortunately, some people get their self-esteem from knowing things that other people don't know. Whereas I would rather get my self-esteem from helping people understand things that I do know. So that's what I like to do. And I then thought, well, here's my Bach braid. What I did here was I wrapped up the present and see what braid I got. So why don't I do it backwards? How about I start with this pattern of ribbons? Can I create a present that is the exactly correct shape to be wrapped up by those ribbons? And I stared at it one day and I thought, do you know, it's a cube. And I did exactly what I do when I discover a mathematical thing. I went, cube! And then about 2 seconds later, I went, oh, I'm probably wrong. And then 2 seconds later, I thought, I bet everyone in the world knows this apart from me. And then 2 seconds after that, I went, well, maybe it's trivial. So it's not trivial. That is, not every braid makes a cube. But I don't know why it's true. I don't know why it happens like this. And I phoned my friend, the one who can sing soprano, alto, tenor, and bass, and I said, oh, and he said, I think it shows that Bach was communing with the spirit of the Platonic solids. And I thought, I don't think that's what it was, actually. But I don't know why it was. I don't know what it's useful for, but I think it's cool. And I think that's enough. I think if something is cool, then that's great. And another thing that's cool is cake. We're going to talk about cake. I love cake, and I love making dessert because dessert is nutritionally useless, and that's why I like making it. Because it serves no purpose except to make me happy, and so I like it. And this is Battenberg cake, which is one of my favorite kinds of cake. It's a very English cake. It's something to do with the crest of the Battenbergs. But the main thing is that there's two colors of cake, and you don't want the same color of cake to touch the same color of cake, because that would be terrible. So this is what it looks like. But it's also a mathematical structure. So I can make a multiplication table for 1 and -1. So here, I'm going to put 1 times 1, which is 1, usually. And here I'm going to put 1 times -1, which is -1. And here I'm going to put -1 times -1, which is 1. So it's a Battenberg cake. I can try this again with adding even and odd numbers. So here I'm going to put what you get if you add an even number to an even number. Even. And if you add an even number to an odd number, odd. And if you add an odd number to an odd number, even. So it's a Battenberg cake. And I can also do this with multiplication of real and imaginary numbers. Now, maybe you don't know what imaginary numbers are, or maybe you've forgotten what imaginary numbers are. But this is what might happen to you when they say in class, you can't take the square root of a negative number. And then the next year they go, okay, now we're going to take the square root of a negative number. So when you do that, you get something that's called an imaginary number, because it's sort of made up, because it doesn't really exist. But does anything really exist? Do real numbers exist? Do I even exist? Do we exist? Do we? I don't know. So imaginary numbers are that. But anyway, it doesn't matter, because I'm going to tell you it makes a Battenberg cake. So that means that a real number times a real number must be real, and a real number times an imaginary number must be imaginary, and an imaginary number times an imaginary number must be real. So it's a Battenberg cake. This is also related to bed flipping. bed flipping or mattress flipping is what you're supposed to do every season to stop your kind of fat bottom from pressing into the same part of the mattress all season. I never do it because I'm much too lazy. But if you were going to do it, then obviously you would write A, B, and C, and D on your mattress to keep track of where you are, right? This is a slight issue with real-life math problems because real-life math problems are often really stupid and obviously contrived and made up just to do some math. And my friends often send me their children's real-life math homework so that we can all laugh at it together. And I know that everyone's trying, but my favorite one was the one she sent me that said, you have 1 meter of string. You use 30 centimeters of it to tie up Joe. You use 35% of it to tie up Eddie. How much do you have left to tie up Sally? And apart from the question of why we're tying people up, 35 centimeters of string is not very long to tie someone up with. So this is a problem with real-life math. Or my other favorite one, you have 85 wild horses, and 17 of them escape. Because yes, I'm very likely to have 85 wild horses at some point in my life. Anyway, if we flip our mattress, we might write letters on it to see where we are. So this is why I've given everyone a little mattress, and we can write a little table of what happens when you do this. So up here is 0 and 0. This is me. This is when you're me and you do nothing ever. So you always stay in the A position. So A is the starting position. And here, we're going to do what happens if you do nothing and then you do rotation. So I'm calling rotation rotating around this way. So you get to B. So this one, start again in the A position. If you do a flip, I'm calling the flip this way, sideways flip. So you get to C. And then if you go back to the A position, here I'm saying this is what you get if you do nothing, and then flop over, flop that way. So you get to D. Okay? So now coming down here is the same thing, because this way around, you do the thing first and you do nothing afterwards. And you can do nothing. It doesn't really make any difference when you do nothing. You can do nothing anytime you want. I love doing nothing. So that gives the same thing. So now here we're going to try doing a rotation and then another rotation. So we rotate, and then we rotate again. We get A. Very good. And then here we're going to start in the A position again. Then you flip over sideways, and you flip over sideways again. You also get A. And then here, you're doing a flop and then another flop. So the flop is flopping over this way, and then you flop over again. You also get A. So that says that if I keep doing the same thing every season, I'll just keep getting back to where I started. So let's try doing something else. Let's try doing a rotation and then a flip. So we do a rotation this way, and then a flip sideways. D, right? And now let's try doing a rotation and then a flop. So we do rotation and then flop. C. And then here we can try doing a flip and then a rotation. So we flip over sideways and then rotate. D. And here, this is the whole point because I get to say flip-flop. So you do a flip, flop, B. And now maybe you can start guessing. So what do you think goes here? Here? C. And what do you think goes here? B. That's right. Now, because we're good mathematicians and not people on the internet, we'll check to see if we're right. Or we could check to see if we're right. I'll tell you we're right. The main question is, how many Battenberg cakes can you see? There's 2 here. There's 2 here. There's the one in the middle. And there's the big one. Because the whole thing is a Battenberg cake, where each small cake was already a Battenberg cake. Here's one. Here are the letters written on it, so you can see how it matches up. I call this the iterated Battenberg cake, because I've iterated the process of Battenbergification. Battenbergification is like painting by numbers. So with the original Battenberg cake, all I had to do was tell you what goes in position 1 and what goes in position 2. So it could be yellow and pink, it could be chocolate and more chocolate, because I always like chocolate. It could be a bunny and another kind of bunny, and now I've Battenbergified a bunny. Or it could be one kind of Battenberg cake and another kind of Battenberg cake. And I've now got the iterated Battenberg cake. And if you make this, you have to cut the cake so carefully to make it fit together. You end up with a lot of leftover cake, and then you make lots of friends. So here is an even more abstract representation of a Battenberg cake. Because all I had to do was tell you what goes in position 1 and what goes in position 2. So it could be yellow and pink, light brown and dark brown, bunny 1 and bunny 2, cake 1 and cake 2. But what is cake 1? Cake 1 was already that, and cake 2 was already this. So why don't I take the picture for cake 1 and put it here where the 1 is? And I can take the picture for cake 2 and put it here where the 2 was. And this is now a very abstract picture of an iterated Battenberg cake. And this is something mathematicians study again. It's a mathematical structure called a tree, because it looks a bit like a tree, like it has a root, it grows up into branches. But the great thing about an abstract tree is that you can think of it as things starting at the top and getting stuck together on the way down as well. Abstract things are very versatile. You can think of them lots of different ways up. So trees come from sticking things together, and we can try this for adding numbers together in 2 different ways. So if I do this, this says add 4 and 4 together first, which makes 8, and then I'm going to add 2 afterwards, and that makes 10. And usually, because we've squashed our math into a one-dimensional straight line, we have to use parentheses now instead of a nice tree picture. But it's really about trees. So on the other side, that says this time I'm going to add the 4 and the 2 together first, which makes 6. And if I add this 4 afterwards, that makes 10 as well, with the parentheses on the other side. And we know these are the same. You might know this as the associative law for addition. And so whatever numbers you feed into this tree, you'll always get the same answer. But this doesn't happen if you use something more subtle than numbers. And when we do higher level math, we use things that are a lot more subtle than numbers. For example, if I mix egg yolks and sugar together, and then afterwards I add some milk and I heat it up, I make custard. Whereas the other way around, if I mix sugar and milk together first, and then I add the egg yolks, I do not make custard. So these things are not the same in the world of custard. Whereas for cake, it doesn't matter so much. So when you're making cake, the usual recipe for cake says cream the sugar and the butter together, and then beat in the eggs, then mix in the flour, and that makes cake if you bake it. But actually, especially if you have an electric whisk, you can just kind of chuck everything in a bowl and go, wah, and it'll be fine. Now, I tried doing it in all the other ways with my art students. We brought all the ingredients for cake into class and we mixed it. So this is the basic little tree moving one branch from left to right. Here are all the ways of doing it. So each of these arrows shows how I move one little branch from left to right. So here, the butter branch moved from left to right, so now it's there. Here, down here, the egg branch moved from left to right. So this recipe says mix the butter and the eggs together first, which is really disgusting. Then you mix in the sugar, and then finally you mix in the flour. But actually, if you beat it hard enough, it still kind of looks like cake batter. And this one down here is quite interesting, because you need 2 bowls. This one, you have to mix the sugar and the butter first, and then you mix the eggs and the flour in a different bowl, and then you mix them together. And if you're lazy like me, you don't want to have to wash an extra bowl. So this is definitely different. Whereas this one over here says mix the eggs and the flour together first, which is also very disgusting. But we did it in class, and we discovered that actually it all comes out kind of looking the same in the end. And we don't have ovens at art school, but we did. I went and talked to the Culinary Institute of America, and they do have ovens. And so we did it there. We baked them. I had 5 pastry chef students who made these cakes in these different ways. We baked them to see what would happen. And what happened was that this one was the usual recipe was definitely the easiest, and it rose the highest. But the other ones were still like cake. They just didn't rise quite as high. And this is different from the custard situation, where if you do it the other way around with custard, it's really not custard. Whereas with this one, they're still cake. They're just slightly different cake. And in math, sometimes things are not exactly, it's not all about right and wrong and equals and not equals. Sometimes things are sort of the same and not totally the same, but you get to decide whether it counts as the same or not. So here, if you're not the one making the cake, maybe you don't care if it was difficult to make. Maybe if you have an electric whisk, then it's all the same anyway. Maybe you're not the one doing the washing up, so it doesn't matter to you that you used an extra bowl. Maybe, if you are making the cake, maybe you don't want your cake batter to go through a stage where it looks like vomit, because it's kind of disgusting. The other thing you can ask yourself here is, what happens if I want to make chocolate cake? Because I always want to make chocolate cake. So you have one more ingredient, which is chocolate. And if you draw all the trees for making chocolate cake, what you get is a shape that looks like this when you stick it together. So this is a pentagon, and it's called the McLean pentagon. And usually you wouldn't see this unless you were doing a PhD in my field, which is category theory. But it's really about chocolate cake. And then if you add an extra ingredient, it gets an extra dimension. And so this has 6 pentagons on it and 3 squares. And if you added one more ingredient, it would become a 4-dimensional shape. And that's a bit more difficult to make. Somebody 3D printed this one for me. I really like it. And in the back of the second half of my book, there's a net, so you can cut it out and make it yourself. So this brings me to what category theory is, which is my field of study. Mathematics is the logical study of how logical things work. And category theory is kind of the mathematics of mathematics. It's quite a recent part of math. It's not about numbers. It's about how math works. So it's about the logical study of how logical things work, which is somewhat looped up on itself. But I like it because I like being able to think logically and think clearly. I think it helps me to live life better. And it also helps me to understand the world better. And it helps me to understand people better, which I think is really important, especially in this day and age. What I do think is that we will never be able to explain the whole world logically. I'm not saying that math can explain everything, but I think that mathematical thinking is at the core of what we understand. Just like you have a physical core, which is here, and if you have a strong core, then it gives you better access to the rest of your muscles. And if you have a strong core of your thinking, then it gives you better access to the rest of your thinking. We'll never be able to understand everything logically, because every time we answer a mathematical question, it creates more questions that we haven't answered yet. So there's always more stuff that we can't answer. And the things I like the best are the things just beyond what we can explain. So in music, I love certain pieces of music. They make me cry, and I'll analyze them to understand why they make me cry, and I can explain a certain amount. But just beyond what I can explain, there's something I can't quite explain. And that's where the most beautiful things are to me. So I have an image that we should try to put as much as we can inside the logical core of what we understand. And as it grows, the surface of it grows. And that surface is where the logic and the inexplicable meet. And so as it grows, we get more and more access to more beautiful things. Thank you.